Hello guys, today we're talking about 2017 AMC10A number 21. Square with side length x is inscribed in a right triangle with sides of length 3, 4, and 5 so that one vertex of the square coincides with the right angle vertex of the triangle. So let's draw this real quick. We have 3, 4, 5 triangle. Coincides with the right angle vertex of the triangle. So something like this. And the square with side length y is inscribed in another right triangle with sides of 3, 4, 5, so we can virtually just copy. Difference is that one side of the square lies on the hypotenuse of the triangle, which means that it's going to look something like this. Sorry, let me fix this actually. So what we have now, x, x, okay, so now we have similar triangles, and we can do x over 4 is equal to 3 minus x over 3. So this goes to 3x is equal to 12 minus 4x. So 7x is equal to 12. We know that x is equal to 12 over 7. So what does this mean? This means that we can start looking at the second one now, because we've already found x. So for the second right triangle, we can tell that this right here is similar to the big triangle. Sorry for the bad graph. I'm going to redraw it in a second. Let's redraw it down here. So what we have is something like this. So this is obviously similar. So you have, this is y. So we have, let's let this be z. So z over 4 is equal to y over 3. So now we know that 3z, so we know that z is equal to 4y over 3. So now we can do the hypotenuse, which is z plus y plus, let's say, a. So we know that we can do another similar triangles on a. And we can do a over 3 is equal to y over 4. So a is equal to 3y over 4. So adding these up, we get 3y over 4 plus 4y over 3 plus y is equal to 5. So this gets us y is equal to 60 over 37. Okay, so that's cool. Since we know both of these lines, what's x over y? 12 over 7 over 60 over 37. That gives us 37 over 35. And that is one of our answers. Thank you. Hello guys, today talking about 2017 AMC10A number 22. So sides of an AB and AC of equilateral triangle ABC are tangent to a circle at points B and C respectively. What fraction of the area of ABC lies outside the circle? So we can start by drawing this line from A down to O, and this will create perpendiculars and right triangles here and here. And this is actually going to create 30, 60, 90 triangles because this cuts the 60-degree angle of A into two parts. So 30, 90, 60. Let's zoom and take a closer look. If we let the radius of the circle be R, then with the properties of the 30, 60, 90 triangle, AB and the side of the equilateral triangle is R root 3. And now we can find the area of ABOC, which is just R root 3 times R over 2 because it's a triangle, and times 2 again because it's two triangles. So this is R squared root 3. But we're trying to find the area that lies outside the circle. So we need to subtract this lune shape. And what is this? So this is 120 degrees because of inscribed angles. So we can do the area of a sector of a circle, which is R squared times pi times 120 over 360. And then what we get from this is that we subtract it from our original. So R squared root 3 minus pi R squared over 3. And this has to be over R squared root 3 squared pi over 4. This is because of the area of an equilateral triangle. And you find the fraction of the area. So we can immediately start by doing this. So we can simplify the bottom by doing this. Simplify the bottom by doing R squared times 3 root 3 over 4. Dividing off the R squareds, we get root 3 minus pi over 3 root 3 over 4. And doing this, we get 4 over 3 minus 4 root 3 pi over 27. Is that one of our answers? Yes, it is. E. And that's your answer. Hello guys, today we're talking about 2017 AMC10A number 23. How many triangles with positive area have all their vertices at points I, j in the coordinate plane, where I and j are integers between 1 and 5 inclusive? So what we can do is we can draw out the 5 points in a graph that's kind of like this. So we have to split the problem into cases. So case 1, the obvious horizontal and vertical lines. So obviously horizontal and vertical lines are straight and they have no positive area because a horizontal line has no area. So there are 10 of these lines, as we can see obviously here. And there's 5 rows. There's 5 rows, and then a line down here, and there's 5 columns. So this is 10 possibilities. And the thing is, from every horizontal line, there's 5 points to choose from, and we have to choose 3 points to make a triangle. So this evens out to 100. So now case 2, diagonals. So diagonals, we can have 1 and 2. So there's only 2 diagonals. So there's 2 times, there's 5 points on each diagonal. If I choose 3, and that is 20. Case 3, 4-point lines. So you might be like, what is a 4-point line? Well, a 4-point line is something like this. These also have area 1 because it's just a line. 4-point line. and 4-point line. So there's only 4 of these. So 4 times, there's 4 points to choose from, and there's 3, you have to choose 3 points out of 4 to make a triangle. So this is 16. Case 4, 3-point lines. So we can paste this graph here again. 3-point lines are, as you can tell, these. 1, 2, 3, 4. There's also 4 of these. 4 and, well, 3, choose 3. So there's only 4 possible triangles. And obviously we can't have 2-point lines because we need 3 points to make a triangle. Case 5, which is the tricky one that a lot of people forget, which is 1/2 or 2 slope lines. And what I mean by this are lines with slope 1/2 or lines with slope 2. What I mean by this is 1, 1, 2. So what I mean by this is something like this. Sorry for the bad graph, but this goes through this point. So all these also work, and they have slope as follows: 1, 2, 3, 4 over 1, 2. So that's the slope 2. So there's 3 on this side. There is 3 on this side. And then we can also do 1, 2, 3, and then 1, 2, 3. So this is a total of 12 lines because there's 3 lines of every color. 3 choose 3 because there's only 3 points on each line, so it's another 12. And this is actually all our cases. So since we're trying to do complementary counting here, since we have to find first positive area, so we get 25, choose 3, which is obviously the total. 25 points, choose 3, triangle. Subtract 100, subtract 20, subtract 16, subtract 4, and subtract 12. 12, 4, 16, 20, and 100. And this evens out to 2148. And that is one of our answers. Our answer is B. Hello guys, today we're talking about 2017 AMC10A number 24. So for certain real numbers a, b, and c, the polynomial g of x equal to x cubed plus ax squared plus x equal to plus 10 has 3 distinct roots, and each root of g of x is also a root of the polynomial f of x equal to 4x to the 4th plus x cubed plus bx squared plus 100x plus c. What is f of 1? So we can write f of x as g of x times x plus r, where r is the 4th root. And we know this because f is 1 degree higher than g, and every root of g of x is also a root of f of x. So what we can do here is we can expand this, and this turns into, obviously, x cubed plus ax squared plus x plus 10 times x plus r. This is equal to f of x. So expanding this out, we get x to the 4th plus ax cubed plus x squared plus 10x plus rx cubed plus ax squared r plus xr plus 10r. This is equal to f of x. So simplifying this, we get x to 4th plus a plus p, sorry, not p, a plus r plus 1 plus AR, 10 plus X, 10 plus R, sorry, plus 10R. And this is equal to x to the fourth plus x cubed plus bx squared plus 100 x plus c. So now we can just equate coefficients. So we have a plus r is equal to, the coefficient of this is 1. 1 plus AR is equal to B. 10 plus R is equal to 100. And 10R is equal to C. So getting from this, we get R is equal to 90. Getting from this, we see that A is equal to negative 89. Getting from this, we see that C is 900. And getting from this, we see that B is negative 8. Sorry for the band header. B is equal to negative 8,009. So we're trying to find the sum of the coefficients of f of x. So we just do 1 plus 1 plus minus plus 9 plus 100 plus 900. So this is pretty simple. We just subtract. We get negative 8,007 plus 1,000. And this is just negative 7,007. And C. Sorry. Hello guys, so we're talking about the 2017 AMC10A number 25. How many integers between 100 and 999 inclusive have the probability that some permutation of its digits is a multiple 11 between 100 and 999? For example, both 121 and 211 have this property. So a multiple 11 that has 3 digits has a property that, well, okay, so let's say the 3-digit number is A, B, C. Well, then if it's a multiple of 11, then A minus B plus C is equal to 0 or 11. And that's just the divisibility by 11 rule. So we could literally just list them out, because if A plus B equals C, A plus B plus, no, sorry, A minus B plus C is equal to 0, then A plus C is equal to B, or A plus C is equal to 11 plus B. There's not many possible choices for this. Alright, so we go case 1, A plus C is equal to B. Okay, so if B is 1, then we can do 1, 0, 1, where let's just 1, 0, 1, and then 2, 0, 2, 1, 1, 2, 3, 0, 3, 1, 2, 3, 4, 0, 4, 1, 3, 4, 2, 2, 4. So what we're doing is we're just doing A plus C is equal to B. So 3 plus 0 is 3. 1 plus 2 is 3. So we can just do this all the way down. There's about maybe 20 pairs, and this is pretty fast. So for 5, 505, well, okay, and then 145, then 235, down to the 6s, 606, 516, 426, 336, 707, 617, 527, 437, 808, 718, 628, 538. So what you do is just progressively just write the pairs that add to 8. So 448. Then we have, and also I'm just not adding commas in the middle to save some time so we can keep this video short and informative for you guys. 909, 819, 729, 639, 549. Well, obviously, this is not all our cases because the issue here is that 549, we didn't include the parts where it's like 459. So let's highlight the ones that have a 0 in it. Well, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 9 times 2 because there's 2 ways to arrange these. Because, for example, 101, you have 101 or 110 because 0 can't be in the front. So it's 9 times 2 is equal to 18. Now, for the numbers that have 3 possibilities are 112, 224, 336, 448, and that's it. So that's 4 times 3. There's 4 numbers that have 3 arrangements. 112, there's 3 arrangements. 211, 121, 112. And then the rest, which we have, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Plus another 16 times 6, which is just 3 factorial ways to arrange them. So this gives us 18 plus 12 plus 96, which is equal to 126. Now, case 2, A plus C is equal to 11 plus B. So we can do the same thing as we did in the front. I'll just speed past B, same format. First we have, obviously, 920, add to 11, 830, 740, 650. Okay, now let's do 1B is 1, so 931, 841, 751. And obviously there's not as many cases as case 1 because B at most is 7. Because if B is 8, then A plus C, there's no way that there's going to equal. So because 11 plus 8 is 19, and the most A and C can be is 9. So let's just hurry up with this. So 661, 942, 852, 762, 953, 843, so not 843, 863, 773, 964, 874, 975, 885, 986, and 997. So now we can just highlight the ones that have zeros in them, which is the first 4. And these have 4 possibilities. They have 920, 290, 902, and 209. So this is 4 times 4. And then now for arrangements with 3, we have 661, 773, 997, and 885. This is 4 times 3. And then the rest we just do as follows. We do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is just 16 plus 12 plus 72, which is equal to 16 plus 84, which is equal to 100. So our total is just 126 plus 100. So the answer is 226. Thank you for watching.